This is a water quality analyzer you can build with an ESP32 that helps determine the pollution level of a river. The device combines 3 different sensors to estimate water quality. The results are displayed in real time on the Arduino IDE serial monitor, allowing you to get measurements within seconds. In this video, you'll learn everything you need to build this project. You'll also see me testing the analyzer on water samples collected from rivers in a big city. Are you ready? Then let's get started. To build this project, we will need the following components: ESP32, pH sensor, turbidity sensor, TDS sensor, step-up converter, 21700 Li-ion battery, resistors, breadboards, and a few jumper wires. As of June 2026, these components cost around $50 excluding shipping and import fees. I've included links to everything in the description below. In addition, we will need a few calibration solutions for the pH and TDS sensors. More specifically, buffer solutions with pH 4, 7, and 10, a conductive solutions rated at 1413 microsiemens per centimeter. Prices vary depending on where you buy them, but you should expect to spend at least another $30 excluding shipping and taxes. Once you have everything ready, we can start assembling the circuit. Begin by placing the ESP32 on the breadboard, then install the resistors. In my case, I'm using 47K and 75K ohm resistors to create a voltage divider. I will explain the reason for that in a moment. Next, connect a step-up converter. Our goal is to generate a stable 5V supply for the entire system, so make sure to adjust the output accordingly. In my case, I had to turn the potentiometer on the converter while monitoring the voltage with a multimeter, as you can see in this clip. Now let's connect the sensors. Start with the pH sensor. Connect its signal wire to the 47K resistor. Then connect that resistor to GPIO 34. The 75K resistor should be connected between the signal line and ground. The voltage divider is necessary because this particular pH sensor can output signals up to 5V, which is too much for an ESP32 input. By using these resistors, we safely reduce the voltage to approximately 3V. If your sensor already outputs a safe voltage range, you can connect it directly to the microcontroller without a voltage divider. Next, connect the DTS sensor to GPIO 35 and the turbidity sensor to GPIO 32. Finally, connect the ESP32 to the power rails. If you need additional help with the wiring, you can follow the schematic clearly displayed on your screen. Once everything is connected, attach the battery. If all the connections are correct, the module should power up immediately. With the hardware finished, it's time to upload the code. But before we continue, I would like to thank today's sponsor, Elecro. If you haven't heard of them before, Elecro is one of the leading providers of open source hardware and manufacturing services. On their website, you'll find everything from ESP32 development boards like the one I used in this project to advanced manufacturing services such as PCB assembly and CNC machining. I've been using their products for quite some time and I've been very satisfied with the quality. So if you are looking for parts or manufacturing service for your next project, I recommend checking them out. You will find a link to their online store in the description below. Thanks to Elecro for supporting this video, and now let's get back to the project. Before taking any measurements, we need to calibrate the pH and TDS sensors. The pH sensor doesn't output a pH value directly. Instead, it generates an analog voltage that must be converted into a pH reading using reference solutions. For this calibration, I use buffer solutions with pH values of 4, 7, and 10. After placing the probe in each solution, I measure voltage ranging from approximately 1.2 volts down to 0.9 volts. This showed that the sensor voltage decreases as the pH increases. Because the calibration point formed an almost perfect straight line, I was able to use a simple linear equation: pH equals to mV plus B, where V is the measured voltage, M is the slope, and B is the offset. Using the calibration data, I calculated a slope of -23.6 and an offset of 32.2. I then added those values to the code. The TDS sensor works in a similar way. It outputs an analog voltage proportional to the conductivity of the water. To calibrate it, I used a standard conductivity solution. Since the conductivity was known beforehand, I could calculate a conversion version of factory that translates sensor voltage into conductivity and then estimate the TDS value in ppm. With both sensors calibrated, we are ready to bring the system to life. To get everything running, you need to upload a sketch to the ESP32. I published the complete code on GitHub and you'll find the link in the description below. Simply download the project, open it in the Arduino IDE, install the required libraries, and click upload. After the board boots up, you will start seeing sensor readings appear on the serial monitor within a few seconds. At that point, the analyzer is ready for real-world testing. To evaluate the project, I collected water from 2 rivers that flow through a big city but don't connect to each other. Even before taking the samples, a quick walk around both rivers gave me some clues about what the analyzer might find. The first river was relatively shallow and the water looked clear enough to see the bottom. There were houses nearby along with visible trash scattered along the banks. What caught my attention, however, were a few pipes discharging some kind of liquid into the river. I couldn't confirm what it was, but it certainly looked suspicious. After spending a few minutes observing the area, I collected a water sample using a plastic bottle, placed it in my bag, and headed toward the second river. The second location was quite different. Despite being inside a residential area, it had much denser vegetation surrounding it. I didn't notice large amounts of trash or any suspicious pipes. What stood out instead was the absence of wildlife. I didn't hear birds, see insects, or notice any obvious signs of animal activity. It felt strangely lifeless. The water also appeared muckier than the first river and had an unpleasant smell. After observing the area for a while, I collected a second sample and returned home to begin testing. The following day, I poured the first sample into the analyzer and waited for the readings to stabilize. After a few seconds, the system classified the sample as polluted, which was consistent with what I expected after seeing those suspicious discharge pipes. The pH sensor reported a value of 12. That's extremely alkaline compared to household bleach. Natural rivers typically don't reach values anywhere near that level. When they do, it's often associated with industrial contamination or improper waste disposal. The conductivity reading indicates relatively low levels of dissolved minerals and salts, which by itself isn't enough to classify the water as polluted. The turbidity sensor reported a low signal suggesting clear water. However, I initially set the thresholds incorrectly in the code, causing the system to classify it as dirty. I later corrected that issue. The second sample produced similar results. The pH reading was around 30, conductivity remained relatively low, and turbidity voltage increased to approximately 0.8 volts, indicating dirtier water. That result was consistent with what I could already observe visually. After completing the test, here's the overall conclusion. My measurement showed pH values above 12 and conductivity around 175 microsiemens per centimeter in both urban rivers. These readings suggest unusually alkaline water, but hobby-grade sensors do have limitations. Laboratory testing would be necessary to verify the exact values. That said, the absence of fish and aquatic plants combined with visible trash and suspicious discharges near one of the rivers makes it entirely plausible that these waterways were polluted. To draw stronger conclusions, I would need to collect samples from multiple locations along each river and repeat the measurements over several days. Comparing those results with professional laboratory equivalent would also help determine how accurate this ESP32-based analyzer really is. My original goal was to make this project fully portable. I designed a custom PCB, added support for the sensors, included a 7-inch touchscreen, and even created a 3D printed enclosure for everything. Unfortunately, things didn't go according to plan. The enclosure had several design flaws, and fitting the display inside it was nearly impossible without modifying the printed parts. The custom PCB also failed. Shortly after pouring it down, the board burned out. After investigating the issue, I discovered that I had accidentally swapped the positive and ground connections, a classic beginner mistake. Rather than giving up, I designed a new shield PCB that allows you to connect all the sensors directly to the ESP32 without relying on breadboards and a mess of jumper wires. I've open sourced their design and you'll find the manufacturing files in the description below. And that's it for today's video. Thank you for watching all the way to the end. If you enjoyed this project, or would like to see a second version that finally becomes the portable water quality analyzer I originally envisioned, let me know in the comments below. I read every comment I receive and I genuinely appreciate the feedback and support. Additionally, if you are working with ESP32 boards, I put together a free guide about 10 common ESP32 mistakes and how to avoid them. In this guide, I cover some of the most common issues beginners and even experienced makers run into, from power supply problems and unreliable sensor readings to upload errors and debugging techniques. You can download it for free by joining my email list. I also send occasional project updates, engineering tips, and resources that can help you build more reliable electronics projects. If that sounds useful, grab your free copy using the link below. And before you leave, I also recommend watching the video currently appearing on your screen. I'm confident it will help you take your maker skills to the next level.